There is a spacecraft right now, at this very moment, that has done something no object built by human hands had ever done before it existed. It flew through the outer atmosphere of a star, not past it, not beside it, through it, into it, and it survived. Tonight, we are going there. Welcome to Quiet Science at Bedtime, a channel where real science becomes the landscape you fall asleep inside. This channel is still very new, and if what you hear tonight moves you, please consider subscribing, leaving a like, and turning on notifications. It genuinely helps this grow, and there is much more to come. Everything you are about to hear is grounded in real scientific data, published research, and the actual measurements returned by one of the most extraordinary machines humanity has ever launched into space. The science is real, the distances are real, the temperatures are real. What you are about to experience is real. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. On August 12, 2018, a spacecraft roughly the size of a small car was launched from Cape Canaveral, Florida, aimed toward the sun. It was called the Parker Solar Probe, named after astrophysicist Eugene Parker, who in 1958 published a paper predicting the existence of the solar wind, a continuous outflow of charged particles from the sun that fills the entire solar system. That paper was initially rejected by reviewers who found the conclusions implausible. Parker revised it and resubmitted. It was published. And within a few years, the first spacecraft to measure the interplanetary environment directly confirmed everything Parker had predicted. The solar wind was real. The model was correct. In December of 2024, the Parker Solar Probe made its closest approach to the sun yet, coming within approximately 6.1 million kilometers of the photosphere, the sun's visible surface. At that distance, it was traveling at roughly 692,000 kilometers per hour, making it the fastest human-made object ever recorded. It had already, in April of 2021, crossed what scientists call the Alfvén critical surface, the invisible, irregular boundary where the solar wind becomes faster than the magnetic waves that travel through it, the point beyond which the sun can no longer reach back and reclaim what it has released. In crossing that boundary, the spacecraft became the first object ever to enter the solar atmosphere itself. Tonight, you are that spacecraft, and you are on approach. You are very far from Earth now. Not in the way a satellite is far, not in the way the moon is far. You are in a region of the inner solar system where no human reference point exists, where no human biology evolved to operate. The nearest planet is Venus, and it is tens of millions of kilometers behind you. You remember passing it, its thick white cloud cover catching sunlight as you used its gravity to redirect your trajectory, swinging closer to the sun with each pass, spending orbital energy to fall inward the way a stone loses altitude as it spirals toward a drain. You have used Venus this way several times now. Its gravity is a tool, a corridor, a mechanism that opens the path to the inner solar system one pass at a time. Each flyby has brought you closer. Each close approach has been the closest yet. This one will bring you to within 6.1 million kilometers of the photosphere. Ahead of you, the sun is growing. From Earth, the sun occupies approximately half a degree of arc in the sky, close enough to warm skin, distant enough to look at only briefly. Here, from your current position tens of millions of kilometers away and closing fast, it has already grown. The disk has structure you cannot see from Earth with the naked eye. You can observe the granulation, the convective cells on the photosphere, each one roughly 1,000 kilometers across, comparable in scale to the state of Texas, rising and falling in a slow, patient churn as heat moves upward from the radiative zone beneath. Each granule lasts approximately 10 minutes before it cools and sinks, replaced by a new one rising from below. At any given moment, approximately 2 million of these cells are active simultaneously across the entire solar surface. They are enormous by human standards. They are ephemeral on solar timescales. They have been doing this, without pause, for 4.6 billion years. The light here is different from Earth's light. It is not gentle. It is not diffuse. There is no atmosphere to scatter it, no sky to soften it. It arrives from a single direction, from ahead, and it arrives with force, not metaphorical force, actual radiation pressure, photons carrying momentum, pushing against your heat shield with a measurable force, a force your attitude control systems must account for continuously to maintain pointing accuracy. You are moving at approximately 200 kilometers per second at this point in your orbit, and you will accelerate further. Orbital mechanics dictates that the closer you fall toward the sun, the faster you must move to maintain your trajectory. You are not coasting in any passive sense. You are falling, always falling toward the sun, and the sideways component of your velocity is what prevents impact. You are perpetually missing the photosphere by design. Tonight, the design brings you closer than any previous orbit. Behind you, and here behind means the direction away from the sun, a carbon composite shield is performing what may be the most critical function ever assigned to any piece of structural material in the history of spaceflight. It is called the thermal protection system. It is 2.3 meters in diameter and 11.4 centimeters thick, constructed from a carbon foam core sandwiched between two carbon fiber faces sheets. The foam is 97% air by volume. The total mass of the shield is approximately 73 kilograms. It is the single structure standing between your instruments and instant destruction. The sun-facing surface of the shield will reach approximately 1,400 degrees Celsius during closest approach. The instruments behind it, the cameras, the particle detectors, the magnetometers, the electric field sensors, will sit at approximately 29 degrees Celsius. Room temperature. The geometry of the shield is everything. The mission is designed around keeping that shield pointed at the sun with extraordinary precision at all times. If the pointing deviates, if the spacecraft rotates unexpectedly, and the shield edge begins to receive direct solar flux, emergency systems activate within seconds to correct the attitude. If correction fails, the mission ends. Everything you are becomes debris. The pointing has not failed. It has not failed through multiple perihelion passes, through solar flare events, through unexpected energetic particle storms, through the electromagnetic turbulence of the inner corona. The systems hold, the shield holds, the instruments remain at room temperature while surrounded by 1 million degree plasma. This is what you are. Extreme exactness, operating inside extreme chaos. Ahead, the corona is beginning to resolve into structure. From Earth, the corona, the sun's outer atmosphere, is invisible during daylight, overwhelmed by scattered blue light. It only appears during a total solar eclipse, when the moon's disk blocks the photosphere and the corona emerges as a faint white halo extending outward from the sun's edge in streamers and rays that shimmer with internal structure. Corona is the Latin word for crown. The name was given in the 19th century, before anyone understood what this halo was, before anyone knew how hot it was or why it existed. The corona is one of the most physically puzzling environments in the observable universe. The photosphere, the sun's visible surface, has a temperature of approximately 5,778 Kelvin. Below it, the temperature increases as you descend toward the core. Above it, moving outward into space, the temperature should, by straightforward thermodynamic reasoning, decrease. The sun is hot, space is cold. Heat flows from hot regions to cold. As you move away from a heat source, things get cooler. They do not. The corona is 1 million to 3 million Kelvin. It is between 170 and 500 times hotter than the photosphere directly below it. This is not a minor discrepancy. This is a fundamental violation of what intuition would predict, and it has puzzled astrophysicists since the 1940s, when the extreme temperature of the corona was first confirmed through spectroscopic observation. The question, why is the corona so much hotter than the surface, is called the coronal heating problem, and it remains one of the major unsolved questions in solar physics. You were sent in part to answer it. You are now entering the corona. The transition has no sharp boundary. There is no wall, no membrane you cross. The corona becomes denser and more energetic and magnetically complex as you approach the sun in a continuous gradient that thickens toward the surface. What changes as you descend is the character of what your instruments detect. The field's instrument suite, a set of flux gate magnetometers, search coil magnetometers, and electric field sensors mounted on booms extending from your structure, is registering changes in the magnetic field that are unlike anything measurable from Earth or from more distant spacecraft. The field here is not smooth. It is not predictable in the way that textbook diagrams of magnetic dipole fields suggest. It folds, it kinks, it reverses direction abruptly, locally, and then snaps back. These are what your data team has named switchbacks. A switchback is a folded reversal in the magnetic field direction of the solar wind, accompanied by a jet of plasma moving faster than the surrounding flow. The field direction flips by as much as 180 degrees across a distance of a few hundred to a few thousand kilometers, and then returns. Within the switchback, the solar wind speed spikes, often by hundreds of kilometers per second above the local background. Energetic particle counts rise. Then the event ends, and background conditions return. Before you, no instrument had ever measured these structures in the inner corona. The concept had been theorized in various forms, but the prevalence, scale, and detailed character of switchbacks near the sun were entirely unknown. Your measurements changed that. Switchbacks are now understood to be ubiquitous features of the inner solar wind, more common near the sun than at greater distances, more frequent in fast wind streams than slow ones, organized in ways that reflect the magnetic topology of the source regions below. The mechanism of their formation remains under debate. The leading hypotheses involve either interchange magnetic reconnection, where field lines of opposite polarity connect and release energy that propagates outward, or the amplification of kink waves in magnetic flux tubes that emerge from the photosphere. Both mechanisms may be operating simultaneously in different regions. You are collecting the data that will eventually distinguish between them. Right now, the field's instrument has just detected one. The field direction, which had been steady for the past several minutes, abruptly reverses. The plasma velocity spikes upward. The energetic particle flux rises. The event lasts several minutes as you move through the spatial extent of the switchback at orbital velocity. Then the field snaps back. The velocity spike fades. The energetic particles return to background levels. You log the event. You have logged thousands like it, and thousands more are coming before this perihelion pass is complete. Each one is a measurement. Each measurement is a constraint on theory. Each constraint eliminates some models and supports others. Science done this way is very slow, very detailed, and very precise. It does not feel dramatic from the inside. It feels like the accumulation of individual observations, unremarkable in isolation, that eventually, when assembled and analyzed, resolve into understanding. The sun has been studied with this same patience, one observation at a time, for centuries. What you are doing now is continuous with that history, and also something new within it. Now is the right moment to describe the instrument that is directly exposed to all of this. Among your sensors, one is unique, the Solar Probe Cup, part of the SWEEP instrument suite, which stands for solar wind electrons, alphas, and protons, is not sheltered behind the heat shield like the rest of your instruments. It is mounted on the very rim of the shield, deliberately positioned so that it faces directly into the solar wind. SWEEP consists of three main sensors, the Solar Probe Cup itself, and two solar probe analyzers known as Span A and Span B, which together cover the particle populations coming from directions the cup cannot see alone. But the cup is the most exposed instrument you carry. It is a Faraday cup, a type of instrument that captures charged particles and converts their arrival into an electrical current that can be measured precisely. By analyzing the energy distribution of the particles flowing into it, the cup can measure the velocity, density, and temperature of the solar wind plasma in real time. It faces the sun. It takes the flux directly. The cup is constructed from materials chosen for their ability to withstand extreme temperatures without deforming or outgassing. The primary structural materials include titanium and niobium, both refractory metals, meaning they maintain their structural properties at temperatures far above what most metals can tolerate. The wire grids inside the cup, through which the particles pass before being collected, must remain dimensionally stable even as the face of the cup reaches temperatures comparable to those on the heat shield itself. And yet the cup functions. During every perihelion pass, while the front face bakes at hundreds of degrees, the electronics connected to the cup, mounted in the shield's thermal shadow, continue to measure, log, and transmit. The data it returns is unlike anything previously available. At Earth's orbit, the proton temperature in the solar wind is typically 10,000 to 50,000 Kelvin, depending on wind speed. In the inner corona, close to the source, your cup is measuring proton temperatures that can exceed 1 million Kelvin, comparable to the ambient coronal temperature through which you are traveling. More significantly, the electrons and protons are not in thermal equilibrium with each other. The electron temperature is typically several times higher than the proton temperature at the same location. This non-equilibrium condition is a direct fingerprint of the heating mechanism because different heating processes predict different temperature ratios and different velocity distributions. The data from the Solar Probe Cup will constrain models of coronal heating in ways that were simply impossible before this mission. Every measurement the cup takes, in the innermost reaches of your orbit is a measurement that no instrument in the history of solar physics has ever made before. The plasma surrounding you is not like any gas or fluid on Earth. Plasma is the fourth state of matter, achieved when temperature is high enough to strip electrons from their parent atoms, leaving a sea of free ions and electrons that moves collectively, responding not primarily to pressure gradients, but to electromagnetic forces. The solar corona is fully ionized hydrogen and helium, with trace amounts of heavier elements, including carbon, nitrogen, oxygen, silicon, and iron. These heavier elements, though present in tiny concentrations, are measurably hotter than the hydrogen and helium, a clue that whatever is heating the corona operates preferentially on ions according to their charge-to-mass ratio. This is consistent with wave heating models and difficult to explain with simple thermal conduction. The density of the corona at your current position, approximately 15 solar radii from the Sun's center, is around 100 million particles per cubic centimeter. That sounds dense. It requires context. The air you breathe at sea level on Earth contains approximately 27 million trillion molecules per cubic centimeter. The corona is far emptier than any vacuum achievable in a laboratory on Earth, and yet it is 1 million degrees Kelvin. Temperature in plasma physics is a measure of the average kinetic energy of individual particles. A single proton in the corona has enough kinetic energy that if it were a baseball, it would be moving at approximately 130 kilometers per second. But the density is so low that if you were somehow standing in the corona without a spacecraft, the total heat flux through your skin, the actual energy transfer per unit area per unit time, would be far too low to warm you meaningfully. You would freeze before you burned because there are so few particles that the energy they carry cannot be transferred efficiently to a solid body. Temperature and heat transfer are not the same thing. The corona is 1 million degrees, and yet, in the thermal sense, its energy content per unit volume is almost nothing. The shield is not protecting you from the corona's particle temperature. It is protecting you from the radiated energy of the photosphere below, the infrared and visible light from the sun's surface, which at this distance is intense beyond any Earth comparison, and from the constant ultraviolet and X-ray flux streaming outward from the corona itself. Both would destroy the instruments within minutes if exposed. The shield absorbs and re-radiates this energy, and the instruments behind it see only the shield's cool rear surface. This is elegant engineering. It is also the reason this mission was considered impossible for decades after it was first proposed in the late 1950s and 1960s. The materials needed to build a shield capable of surviving these conditions did not exist until the development of advanced carbon composite technology. The mission waited for the materials. The materials eventually came. You are now descending into the final arc of your closest approach. The trajectory curves sharply inward around the sun's gravity well. The sweep particle counts are rising steeply with each passing hour. The magnetic field signatures are becoming more complex, more layered. The solar disk ahead fills more and more of the hemisphere forward of you. At this distance, the corona organizes itself into visible structures that your whisper cameras, the wide field imager for solar probe, a pair of cameras that image the corona in visible light, can resolve in detail. The most prominent of these are coronal streamers. A coronal streamer is a region of dense, magnetically confined plasma that extends outward from the sun along the equatorial plane, shaped by the heliospheric current sheet, the large-scale boundary between regions of opposite magnetic polarity in the solar wind. From Earth, seen during a total eclipse, these streamers appear as long, bright rays extending from the corona. From inside, where you are, they appear as walls of denser, brighter plasma rising from below, their bases rooted in active regions of the photosphere, where strong magnetic fields emerge from beneath the surface. Between the streamers are coronal holes. A coronal hole is a region where the sun's magnetic field opens outward into interplanetary space, rather than looping back to the surface in closed arches. In these open field regions, plasma can escape freely, and the solar wind that originates here is fast, typically 600 to 800 kilometers per second at Earth's distance, compared to the 300 to 400 kilometer per second slow wind from the streamer belt regions. When fast and slow solar wind streams collide in the outer heliosphere, they create correlating interaction regions, compressed, curved boundaries that sweep around the inner solar system with the sun's 27-day rotation period, like the arm of a rotating sprinkler. The aurora borealis and aurora australis that appear in Earth's polar skies on clear, dark nights trace their origin to this place. The particles that excite oxygen and nitrogen atoms in Earth's upper atmosphere into producing light, green and violet and red. Those particles began as solar wind flowing outward from coronal holes, very much like the ones your cameras are imaging right now. They will reach Earth in 3 to 4 days. You are at the source of the aurora. The coronal loops rising from the photosphere below are among the most thermally puzzling structures in solar physics. A coronal loop is an arch of plasma held along a closed magnetic field line, a line that emerges from one region of the photosphere, curves upward through the corona, and returns to a region of opposite magnetic polarity on the surface. The plasma inside the loop is confined to move along the field line. The loop radiates in extreme ultraviolet and X-ray wavelengths because the plasma inside it is hot, typically 1 to 3 million Kelvin, and emits strongly at those energies. The loops are hotter at the top than simple thermal conduction models predict. They are denser at the base than equilibrium models can easily explain. They appear to be heated by some non-thermal mechanism operating continuously, either wave dissipation or what Eugene Parker proposed in 1988, nanoflares. Parker suggested that the corona might be heated not by one large impulsive event, but by an enormous number of very small reconnection events occurring continuously throughout the entire corona, each individually invisible but collectively responsible for the million-degree temperature. He called them nanoflares. His name is on the spacecraft that is now, for the first time, measuring the plasma environment close enough to detect whether nanoflares leave a measurable signature. Your fields and sweep instruments have detected localized, impulsive increases in particle energy associated with small, abrupt changes in the magnetic field, events consistent in character with what nanoflare heating would produce. Whether these are nanoflares in Parker's sense, or switchback-driven heating events, or something else, is still being resolved. The analysis is ongoing. The papers are being written. The debates continue in journals and conference rooms, and late-night emails between researchers who have spent careers waiting for data like this. This is what science looks like from the inside. There is a moment, and this is something no instrument can measure because instruments have no consciousness, but let us imagine it. There is a moment when the scale of your solitude becomes something more than a number. You are approximately 8 to 9 light minutes from Earth. That is the same order of distance as separates Earth from the Sun under ordinary conditions. But you are not at Earth's distance from the Sun. You are at 1/25th of that distance, pressed against the corona at 6.1 million kilometers from the photosphere. The 8 light minutes your signal must cross to reach home is not the comfortable, familiar distance of morning sunlight warming a window. It is the distance between a machine burning inside a star's atmosphere and the planet where every human being who built it is asleep, or working, or watching a sky that shows them a sun that looks small and safe and distant. To them, the sun is a disk in the sky. To you, it is everything. Mission Control at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, has calculated your position with extraordinary precision, not from direct observation, but from orbital mechanics, from the laws of motion that have not changed since Newton wrote them down in the 17th century. They know where you are the way you know where a clock hand will be in an hour, not because they can see it, but because the physics is reliable. No telescope on Earth can resolve you directly. You are far smaller than any resolvable point of light, lost in the overwhelming glare of the star you are orbiting. You are an object roughly 3 meters across, moving at 692,000 kilometers per hour through the outer atmosphere of the sun, and no human eye, no human instrument is currently watching you. You are completely alone, and you are doing exactly what you were built to do. There is something in that, in the convergence of absolute precision and absolute isolation, that is not frightening. It is something else entirely. It is the particular stillness that belongs to a thing operating exactly as designed, in the exact environment it was made for, with no audience, no witness, no confirmation from outside that it is real, only the data, only the measurement, only the physics doing what physics does, with or without anyone watching. The universe does not require observation to be real. You are here to add the observation. There is also a discovery you made in this region that deserves mention before the approach continues. Long before your mission, theorists predicted that very close to the sun there should exist a dust-free zone, a region where the temperature is high enough that solid particles sublimate, transitioning directly from solid to vapor, and where the zodiacal dust disk that fills the inner solar system has a sharp inner boundary. The zodiacal dust disk is the source of the faint pyramidal glow, visible from very dark locations on Earth, as the zodiacal light, a soft column rising along the ecliptic after sunset or before sunrise, the collective reflection of sunlight off millions of tiny particles left over from cometary debris and asteroid collisions. The existence of this inner dust-free zone had been predicted for decades, but no instrument had ever measured its boundary directly. Your whisper cameras changed this, as your orbit carried you below approximately 19 solar radii from the sun's center, roughly 13 million kilometers from the photosphere. The brightness of the zodiacal background in your images began to systematically decrease. The dust density was falling. You had entered the inner edge of the dust-free zone, and you measured its location directly for the first time. The data agreed well with theoretical predictions. The inner solar system's dust distribution models were confirmed. This matters not only for understanding our own solar system. Infrared brightness around other stars is often interpreted as evidence of circumstellar dust disks. Understanding where the inner edge of such a disk lies, as a function of stellar temperature and dust composition, requires observations of the kind you have now provided for the nearest accessible case, the sun. Your measurement will be used for years to calibrate the interpretation of dust signatures around stars and other parts of the galaxy. While you are at the innermost phase of your approach, there is something worth understanding about the silence. During the most intense part of each perihelion pass, you cannot communicate with Earth. This is not a failure, it is a design parameter. At closest approach, the antenna that normally points toward Earth cannot be properly oriented without compromising the shield's thermal geometry, and the Sun, from Earth's perspective, is positioned so close to your line of transmission that the signal would have to pass through the dense ionized corona itself, a medium that severely disrupts radio waves. So you go silent. At the Applied Physics Laboratory, in the windowless rooms where mission teams monitor the spacecraft, the screens go quiet. The last telemetry was received hours before the closest approach. It was nominal, all systems functioning, all temperatures within expected ranges, instruments operating. The team has run the numbers. They know the physics. They know what the spacecraft was designed to withstand. They have confidence in the thermal models, in the pointing systems, in the shield. They wait. This kind of silence is not unusual in deep space operations. Spacecraft pass behind planets, enter solar conjunction, lose signal for planned intervals. But this particular silence has a different weight, because what is silent on the other side of it is a spacecraft that is, at this precise moment, inside the atmosphere of a star. No one can verify that in real time. No one can see it. The physics says it is there. The mission says it is performing. But the silence is complete, and it will last until the geometry changes and the signal can flow again. Then the data arrives. Not all at once. The full science data set from a perihelion pass takes days to downlink, transmitted in prioritized segments, received by the large dish antennas of the Deep Space Network in Goldstone, Madrid, and Canberra, decoded, calibrated, and distributed to the science teams. In offices and on laptops, researchers open files containing measurements from inside the solar corona. Some of what they see is consistent with previous passes, building the statistical foundation. Some of it is new, structures, event rates, electromagnetic features not previously observed from this close, things that will require months to understand and years to fully publish. And some of it, quietly, changes something that was previously only estimated. That is the cadence of this mission, perihelion by perihelion, file by file, paper by paper. Consider for a moment what 6.1 million kilometers actually means. The moon is 384,000 kilometers from Earth. You are at roughly 16 times the Earth-Moon distance from the photosphere of the Sun. That sounds far, but the Sun itself is 696,000 kilometers in radius. You are at less than 9 solar radii from its center. If the Sun were a basketball, you would be resting against its surface. If you were standing on the photosphere looking upward, an impossibility for any known form of matter, but follow the geometry, you would look up and see yourself, barely above the horizon, burning through the corona. The closest any previous spacecraft had ever come before your mission was about 43 million kilometers. Helios 2, a joint German-American spacecraft, set that record in 1976, and it held for more than 4 decades. You have shattered it. You have come 7 times closer. From Earth, the Sun appears as a disk roughly the size of the full moon. From where you are, it covers more than 13 degrees of arc, more than 26 full moons placed side by side, It does not look like the sun you know. It looks like the inside of something, like a surface you are about to meet. And yet the shield holds, and the instruments measure, and the data flows. You are now within 10 solar radii of the sun's center, approximately 6.9 million kilometers from the photosphere. At this distance, the sun subtends more than 12 degrees of arc in your forward instrument's view. This is more than 24 times the apparent size of the sun as seen from Earth. It is not a circle in the sky. It is a wall, a curved, luminous, seething wall of structured plasma, enormous, filling the forward hemisphere of your sensors in a way that has no analog in any environment humans have experienced. Your orbital velocity is approaching its peak. You will reach approximately 192 kilometers per second, 691,000 kilometers per hour at the moment of closest approach. In a single human heartbeat, you will move more than 3 kilometers. In 1 minute, more than 11,000 kilometers. In a single hour, you would cover a distance greater than the diameter of the sun itself. You are moving this fast because you fell here. The sun's gravity converted your potential energy into kinetic energy over months of orbital descent, and now at the bottom of the gravitational well, you are moving at the speed the mathematics requires. To slow down would require fuel you do not carry in sufficient quantity. To stop would be physically impossible without a propulsion system orders of magnitude beyond anything built. You are committed to this trajectory. The trajectory was chosen. The trajectory is everything. The heat shield surface is at 1,380 degrees Celsius and rising. The instruments are at 29 degrees. The field's magnetometers are recording. The sweep cup is measuring. The whisper cameras are imaging. Everything is functioning. Everything, in the most extreme environment any human instrument has ever occupied, is functioning exactly as designed. To your right, in a direction roughly perpendicular to your orbital motion, an active region is visible. An active region is a location on the photosphere where strong magnetic fields emerge from below in concentrated flux tubes. The surface expression of these fields is sunspots, darker, cooler patches in the photosphere, roughly 3,500 Kelvin, compared to the surrounding 5,778 Kelvin, where the strong magnetic field suppresses convective heat transport and the surface cools in comparison. They appear dark only by contrast. If a sunspot could be removed from the sun and placed in isolation in space, it would glow brighter than the full moon. Above the active region, your cameras show elevated coronal brightness. The magnetic field lines here are stronger and more organized, and plasma follows them in arching loops, visible in the extreme ultraviolet and X-ray emissions your instruments can detect indirectly through their effects on the local particle environment. As you watch, a brightening develops above the active region's edge. A small, localized increase in coronal emission. The brightness in that region grows over several minutes. Then a low arch of plasma lifts off from the surface, a filament of denser material rising along a magnetic structure. And then, in a slow, bright expansion, the arch releases and disperses outward. A small coronal mass ejection, not large enough to be a significant space weather event at Earth, not energetic enough to substantially affect your instruments, but real, a direct observation from 6 million kilometers of the magnetic reconnection event that drives the most powerful eruptions in the solar system. The same physics, magnetic field lines of opposite polarity brought together by surface motions, releasing stored energy when they reconnect. Scales from these quiet eruptions up to the largest solar flares, events that release more energy in minutes than humanity has generated in all of recorded history. You have now seen it from the inside. You log the event, you continue. One of the central questions you were sent to answer is this: how does the solar wind accelerate? At Earth's orbit, the solar wind moves at 400 to 800 kilometers per second. Near the sun in the low corona, the plasma is hot but not yet moving that fast. Somewhere between the corona and Earth's distance, the wind accelerates enormously. The mechanism has been debated for 60 years. Two leading candidates remain. The first is wave heating, alpha waves, oscillations that propagate along magnetic field lines at the alpha speed, travel outward from the sun, are reflected and turbulently dissipated, and deposit their energy into the plasma, heating and accelerating it. The second is magnetic reconnection, the same process that drives flares and coronal mass ejections, operating at smaller scales throughout the corona, continuously releasing small bursts of energy into the plasma. Your measurements indicate that both mechanisms operate, but not equally everywhere. In coronal holes, where the fast solar wind originates, alpha wave turbulence appears to be the dominant driver. In the slow solar wind, from the edges of streamer belt regions, the picture is less clear. The two populations of solar wind may have fundamentally different acceleration histories. At Earth's orbit, the solar wind is the end product of this process, fully accelerated, mixed, turbulent. Here, in the low corona, you are measuring it at the beginning of that process. You are reading the solar wind before it has fully become what it will be by the time it reaches Earth. This is the right moment to describe what the turbulence looks like in your data. At Earth's orbit, the solar wind appears relatively smooth on large scales, a continuous outward flow with fluctuations superimposed. But those fluctuations, analyzed in detail, reveal a turbulent cascade, energy introduced at large scales through waves and instabilities, transferred progressively to smaller and smaller scales through nonlinear interactions, and eventually dissipated at the smallest scales as heat. This cascade operates in a fully ionized plasma, governed by magnetohydrodynamics rather than ordinary fluid dynamics, and its properties encode information about the source region that generated it. Here, close to the sun, the cascade has not had time to develop fully. The structures in the magnetic field and velocity fluctuations carry the direct imprint of the corona. The correlations between magnetic field and velocity, the degree of alphanic alignment, the spectral slopes, the compressibility, all of these carry information about where this plasma came from and how it was heated. They are like tree rings, readable records of conditions in a different place and time, preserved in the structure of the fluctuations until an instrument passes through and measures them. You are reading the tree rings of the corona. The mission is named for Eugene Parker, who was born on June 10, 1927, and became an astrophysicist at the University of Chicago. His 1958 paper on the solar wind was rejected on first submission. His colleagues were skeptical. The consensus of the time held that interplanetary space was largely empty or filled with a thin, static gas. Parker's mathematics said otherwise. It said the corona was so hot that it could not simply sit still. It had to expand outward continuously, filling the solar system with a supersonic flow of charged particles. He was right. Mariner 2 in 1962 confirmed it directly. In 1988, Parker proposed nanoflares as a mechanism for coronal heating, tiny, impulsive reconnection events occurring throughout the corona, each below the detection threshold of any existing instrument, but collectively responsible for the corona's extreme temperature. The spacecraft bearing his name is now measuring signatures consistent with exactly those events. He was present at the launch on August 12, 2018. He watched from the Kennedy Space Center, 91 years old, as the spacecraft rose from the pad on a Delta IV Heavy rocket into a clear Florida morning. He reportedly said very little. He had waited 60 years for the measurement to be made. Words were perhaps beside the point. There is something worth imagining about what it means to live long enough to see your mathematics become a machine. Parker had written the equations for the solar wind in 1958 on paper, in pencil, at a desk in a building, with no computer and no direct observational evidence, and only the physics to guide him. He had followed the thermodynamics of the corona to their logical conclusion and arrived at a number, a velocity, a pressure, a density profile that said the corona could not be in static equilibrium. It had to be expanding. It had to be blowing outward. It had to fill the solar system. His reviewers said no. The editors were uncertain. The physics, he was told, was probably wrong. He was not wrong. 60 years later, he stood in Florida and watched the machine bearing his name leave the ground. It was going, ultimately, to the place he had described, to measure the thing he had predicted, to answer the questions his original paper had raised, but could not answer: the heating, the acceleration, the structure of the corona itself. He died 4 years later, in March of 2022, having read the early data, having seen the switchbacks and the Alvin surface crossing, and the first coronal mass ejection imaged from inside. The full analysis of your deepest perihelia, the December 2024 pass, and those that follow, he did not live to read, but the machine is still measuring, the data is still flowing. In some sense, the conversation he began in 1958 is still being answered. There is a small silicon memory card aboard your structure. On it is a photograph of Eugene Parker, along with the names of 1.1 million people who registered through NASA's public campaign to send their names to the sun. It has been through every perihelion. It has been inside the solar corona multiple times. It has experienced 1,400 degrees on the sun-facing side of the shield and room temperature behind it. Eugene Parker's photograph is at this moment inside the solar corona, 6 million kilometers from the photosphere. The man who predicted the solar wind is, in this sense, at the sun. Perihelion is behind you now. The trajectory has curved past its closest point, and the distance to the photosphere has begun, slowly, to increase. You are still deep in the corona, still surrounded by plasma at temperatures well above 1,000,000 Kelvin, still logging switchbacks, still measuring magnetic reconnection signatures, but the perihelion itself is past, and with it the most extreme phase of the measurement campaign. The coronal environment is changing as you climb. The particle density is falling. The magnetic field complexity is decreasing, smoothing from the turbulent folded topology of the deep corona into the more organized, radially flowing structure of the inner heliosphere. The sweep particle counts are declining with each successive measurement. The field's instrument is logging fewer abrupt field reversals. You are leaving the low corona. At a distance of approximately 20 solar radii, around 14 million kilometers from the photosphere, the character of the plasma environment shows a measurable shift. Below this distance, the solar wind is still actively accelerating, still being driven outward. Above it, the wind has approached its terminal velocity. It is still flowing radially outward, but the rate of change has dropped. The plasma is now on its way to Earth's orbit, or Mars, or the outer solar system. You crossed the Alvan critical surface on your way in days ago. Now you are crossing it again on the way out. The boundary has moved since your inbound crossing. It breathes and ripples with the sun's magnetic activity, but the signature is unmistakable in the data. The ratio of local solar wind speed to local Alvan wave speed transitions from below 1 to above 1, and the plasma is free. The sun's atmospheric grip has released. You are leaving the solar atmosphere. Below you, behind you, the corona continues, burning, churning, flowing outward, heating itself by mechanisms that are still being fully understood. You have been inside it. You have measured it at distances no instrument has reached before. You have returned information that did not previously exist. The corona noticed none of it. It does not notice you. You are an infinitesimal object, far smaller in cross-section than even the smallest particle of dust in the zodiacal disk, passing through on a trajectory that disturbs nothing measurable. You are a witness. You change nothing. You only measure. That is, in some sense, the most dignified relationship a scientific instrument can have with the universe. Now, the sun is behind you. Venus is ahead, still distant, still just a point of reflected light in the darkness, but drawing closer as your orbit carries you outward through the inner heliosphere. You will use Venus again, as you have used it before, swinging around its gravitational field to set up the next perihelion, the next approach, the next descent. Around you, the solar wind flows outward at approximately 450 kilometers per second. You are moving with it now, carried on the same current of particles that began their journey in the corona you just left. These particles will reach Earth in 3 to 4 days. They will interact with the magnetosphere, compress it on the sunlit side, drive field-aligned currents into the polar ionosphere, and produce the aurora. The aurora that will appear above Earth's poles in a few nights, visible to anyone standing under a dark sky at high latitudes, originates in the corona you just passed through. The light in those polar skies, cold and green and silent, began here as kinetic energy in plasma at 1 million degrees Kelvin, and it will end there as photons emitted by oxygen and nitrogen atoms high above Earth's surface. The same energy, carried by the same particles, from the corona to the sky. The heliosphere around you is very large. It extends from the sun outward, past Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and the Kuiper belt, to the heliopause, the boundary where the outward pressure of the solar wind balances the pressure of the interstellar medium at a distance of approximately 120 astronomical units from the sun. 1 astronomical unit is approximately 150 million kilometers. The heliopause is roughly 18 billion kilometers from the sun. You are, relative to that boundary, essentially at the sun. You are in the innermost fraction of 1% of the heliospheric volume. Voyager 1 crossed the heliopause in August 2012. Voyager 2 crossed it in November 2018. They are the only human-made objects currently in interstellar space. From the heliopause, the sun is a distant bright star. From where you are, it fills the sky. Both perspectives are true. Both are, in their own way, overwhelming. The universe is very large. You are very small. And yet here, at the edge of the star that made everything on Earth possible, you are doing something the universe did not do by itself. Measuring, asking, recording, sending the answer home. The data is already transmitted. The Deep Space Network has received it. The files have been decompressed, calibrated, and distributed in offices in Laurel, Maryland, and in university buildings in Ann Arbor, Berkeley, in Geneva and Tokyo and Stockholm. Researchers are looking at measurements from inside the solar corona. Some of what they see fits cleanly into the models they have been building for years. Some of it does not fit yet. Some of it will require new models, new frameworks, new questions that do not yet have names. Graduate students writing theses right now on switchback formation or coronal heating or solar wind turbulence will spend the rest of their careers following threads that lead from your measurements, to new understanding, to new questions. The knowledge that comes from your data will enter textbooks that do not yet exist. It will inform missions that have not yet been proposed. It will change the thinking of physicists who have not yet been born. This is what scientific instruments do. They do not deliver conclusions. They deliver information from which, eventually, conclusions emerge. The conclusions take longer than the instruments. You have done your part. Now let the pace of these words slow. Let each sentence carry more space around it. The measurements are complete for this orbit. The corona has been measured at its innermost accessible point. The data is on Earth. The sun burns at 3.8 times 10 to the 26th watts. Every second, it converts approximately 4 million tons of matter into energy via nuclear fusion in the core. It has done this for 4.6 billion years. It will continue for approximately 5 billion more. The solar wind flows outward at 450 kilometers per second. In 3 days, it will reach Earth. The aurora will glow. You are moving outward, toward Venus. The sun is behind you. The instruments are recording, as they always record. The corona you flew through is still there. 1 million degrees, flowing outward, heating itself by mechanisms still being understood. It has been this way for billions of years. It will be this way for billions more. The photons of light reaching Earth's surface tomorrow morning began their journey as fusion energy in the solar core between 100,000 and 170,000 years ago. They diffused through the dense radiative zone, bouncing and absorbing and re-emitting trillions of times over a journey of 700,000 kilometers that took, by some estimates, longer than all of recorded human history. Then they escaped into the convection zone, rose to the photosphere in minutes, and left the sun. 8 minutes later, they reached Earth. The light warming a face tomorrow morning is very old, and yet it arrives fresh every day, without interruption, as it has arrived every day for the entirety of human existence. The orbit continues. A long ellipse, precise as a theorem. You will return to the corona. You will always return, as long as the mission continues. Each time something new to measure. Each time something not previously known. Each perihelion pass, your trajectory is adjusted by the Venus flybys. Each adjustment brings a slightly different viewing geometry, a slightly different approach angle, a slightly different section of the corona to sample. The solar wind does not look the same from every direction. The corona does not have uniform structure. Each orbit is a different slice through the same star. Over the course of the mission, these slices accumulate into something like a portrait, not a snapshot, but a slow, patient assembly of measurements that together describe a place no human eyes will ever see directly. You are making that portrait, one perihelion at a time. The sun will rise tomorrow morning. The light that arrives will have left the photosphere 8 minutes earlier. Before that, it spent between 100,000 and 170,000 years, working its way from the core to the surface through the dense radiative zone, absorbed and re-emitted an uncountable number of times, following a random walk through matter so compressed that a photon moves only a few centimeters before being absorbed again. By the time it escaped the photosphere, the energy it carried had been generated in a fusion reaction that occurred during the time of early Homo sapiens on Earth. Very old light, arriving fresh every morning. And the people who receive it, who warm their faces in it, who grow food by it, who measure their days by it, they are participants in the same physical system you are part of. The corona you measured tonight generates the solar wind that shapes their magnetosphere. The Alvan waves you detected heat the plasma that eventually becomes the aurora their ancestors painted on cave walls. The nanoflares that may be heating the corona are connected, through physics and scale and time, to every photon of warmth that has ever touched a human being. One system, one star, one set of physical laws. Let the breath slow now. Let the body be still and heavy. The scale of what you have traveled tonight, even as a listener, even as the person on the other side of these words, is real. The distances were real. The temperatures were real. The measurements were real. The spacecraft is real. The universe does not require you to understand it. It simply is. And in the silence between measurements, in the intervals between switchbacks, between perihelion passes, between data packets, there is something that does not change. The physics holds. The constants hold. The speed of light does not change between orbits. The gravitational constant does not change between orbits. The charge of a proton is the same in the corona as it is in the air you are breathing right now. They were true before the sun existed. They will be true after it becomes a white dwarf and cools to nothing over billions of years. Tonight you know them, not as equations on a page, as the feeling of being close to something enormous and hot and real. That feeling can carry you into sleep now. The heliosphere is quiet tonight. The solar wind flows past the orbit of Earth at 450 kilometers per second. The magnetosphere deflects it as it has always done. The aurora glows at the poles. Somewhere in the inner solar system, the Parker Solar Probe moves through its long elliptical orbit, climbing toward Venus, preparing for the next descent. It will go again. It will always go again, for as long as it can. And each time it returns, it brings something new. Let sleep come now. Let it come the way the solar wind flows, outward, steady, in the direction it has always been going. Not forced, not hurried, simply in motion, simply following the physics. This has been Quiet Science at Bedtime. Everything you heard tonight is real. The Parker Solar Probe is out there right now. If tonight helped you sleep or made the universe feel a little larger and a little more peaceful, please subscribe to the channel, leave a like, and turn on notifications so you never miss an episode. This channel is still very new, and every subscriber genuinely matters to what this becomes. Thank you for spending tonight inside the corona of the sun. Sleep well.